Hello everyone. In this video we are going to do a demonstration of how to use tools in Jamovi to help us out with problems utilizing the central limit theorem. Okay, so quick review of our central limit theorem. Remember that the central limit theorem basically states that a sampling distribution from any population will be approximately normal as long as one or two things kind of hold true. A, we have a big enough sample size. The rough cutoff is at least 30 observations. And then the other is that if the original distribution is normal, then the sampling distribution is going to be normal as well. All right, so a little cryptic, but what it essentially means is that we can actually make some really cool conclusions about the mean as long as we have a big enough sample size. And if we have some information about the original population. Now, we don't need to know what the original distribution actually is, but we do need to know a few things. So let's go ahead and look at our scenario. So it says, hey, remember Harry from last time? Well, as he was working with Jack, another trainer came up to him and revealed the secrets of the central limit theorem. Harry was so impressed he decided he wanted to crunch some numbers. During these games, they have a row-off to see how far athletes can row in 4 minutes. At this competition, they have an event called Battle of the North Sea, where athletes are randomly assigned to teams and compete in Viking-inspired rowing events. Overall, we know that the average 4-minute row time is about 700 meters with a variance of 140,100 meters squared. And they know that the distances are not normally distributed. And then report answers accurate to 3 decimal places. So what we're going to start with is we're actually going to start again using this R editor. And we're going to need to do just a little bit. So first thing we're going to do is we're going to type in a little line that's going to allow our decimal places to be sufficient. So we're just going to type in options and then digits equals, and we're going to put in like, I think 6 or 7 will be sufficient. If you need more decimal places, just change that digits up. All right, now let's go ahead and start gathering some of the data that we have. So we're doing this 4-minute row. The 4 minutes in this one actually doesn't matter. It's just talking about the particular event that we're doing. But we do know that the mu for this distribution is 700. And we know that the variance that was given to us was this 240,100 meters squared, which means that the standard deviation is equal to the square root of the variance. And if we want to see that standard deviation, we just need to type out standard deviation. Now, it also told us that it is not normal, like explicitly told us that it's not normal. But because we have the true mean, we have the true variance, and we have a big enough sample size, when we get down to these questions, we're going to be able to utilize the normal distribution for the distribution of the means in our sampling distribution. Okay, so let's look at this first question and we'll see what's going on. So it says, for the first event, they are grouped into teams of 88. So that is in reference to the sample size, N1 equals 88. All right, and the next one, it says, what percent of teams can average above 739 meters? So that's going to be our first observation, X1, and this is 739. Now, when we are doing our calculations, we need to remember that we need to, when we're using our central limit theorem, we need to calculate out our standard error. So our standard error is just going to be very simply the original standard deviation divided by the square root of the sample size. And we can see that by just typing out SC1. Okay, so we're going to need all of these in order to answer this question. What percent of teams can average above 739 meters? Let's just do this running. So you can either hit the green arrow, or you can do like Control-Shift-Run, or Control-Shift-Enter. Now, one other thing that we want to do, go ahead and click on the gear icon, and we want to show code and output. And this way we can reference it as we are doing other things as well. Okay, so now we are ready to go to this distraction, go to normal distribution. And here, now we have our normal distribution. We can set up like our mean and our standard deviation. So the mean that we are going to use here is that true mean of 700. Now the standard deviation here is not the original standard deviation, because we know the original standard deviation is not normal. It told us as much. But the sampling distribution, when we are talking about the distribution of means of teams of 88 at a time, actually follows this standard error 1. That's our new standard deviation. So we can type that in like 52.23418. That'll give us our distribution. And we are going to compute a probability. It says what percent of teams can average above 739. So we can type in 739 here, and we want to know greater than it. And the answer that we get is 0.228, or there's like a 22.8% probability that a team can average above this value. Okay? Next, how many standard deviations away from the mean is the target distance for ramming speed? All right, so let's go back to our R editor. Now let's actually do this calculation. So we're going to type Z1. Remember, this is a Z-score equation. Z-score. And it's a very simple one. It's just our x1 minus mu divided by the standard error for this first scenario, SE1. And to display it, we're just going to type Z1, and we can hit run again. And we get the Z-score of 0.7466, or they are 0.7466 standard deviations away from the mean. Okay, for the second event, they group into teams of 37. Okay, and then we're going to do the same thing. They're still saying what percent of teams can average above 739. So the nice thing is that we can actually kind of do a copy, and I'm going to paste this down. And I'm going to change the N1s to N2s and the SE1s to SE2s all through. The code, though, is all the same, because we're doing the exact same thing, but just with a different sample size. And this sample size is now going to be 37. And we can do our running it again, and it'll give us a new standard error that we need. And it also asks us how many standard deviations away from the mean is that target distance for a rating party. And if we click that, it's 0.484 standard deviations away. Okay, now let's go ahead and go back to our normal distribution. And let's change. The only thing that we need to change here is the standard deviation, because this is going to be our standard error 2, or 80.5555. And once we do that, it gives us that there's a 30% chance that a randomly selected team is going to be able to do better than 739. There we go, 30.314. Scrolling on down. Okay, so Jack, remember he was Promise Athletes from last time, wants to know what his team's average should be if they want to be in the top 5% of both ramming, speed, and rating parties. Okay, so that's a quantile question, so let's go ahead and click on quantile. We want the cumulative quantile, and we want to be in the top 5%, which means that from the left, we want to go to 0.95, and that will give us our top speed. Now, this one is with regard to using the standard deviation of the second event. So that's one's for the rating party, because we use the standard deviation of the 80.55. And we get 832. Now, if we're going to do the ramming speed, we need to change the standard error back to the first one. So our first standard error, let's get rid of that, is this 52.23418. Enter. And this upper quantile is this 785. And there we go. All right, last part. Okay, why is the distance from from the mean to the top 5% less for ramming speed than for rating party? Okay, so consider the following graphics. All right, so what this is basically helping you realize is that it's harder to get away from the mean when you have a big sample instead of a small sample. So think of this. If you were to randomly select, 2 people in the world, is it possible that, both of them are over 6'10"? And you're like, yeah, it's possible. It's not crazy. It's a little rare, but it's hard. Now, what if I told you, what if I were to randomly select 1,000 people in the world and their average heights were all over 6'10"? You're like, ooh, that would be really hard to get over, or to get 1,000 people with an average height of over 6'10". And so if you come down and we look at the key, it says more rowers and ramming speeds means the standard error is smaller, which makes the distance to the top 5% from the mean is closer than that of rating party. Okay, anyhow, that is how we can use our central limit theorem with our means for an original distribution that in fact is not normally distributed. And we were able to do that because the sample sizes were both at least 30. All right, best of luck to you on your own applications of the central limit theorem.